Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This is where we left off. Any other things come to mind that mostly want to, sort of focus it on in terms of understanding the theory, make sure the base is there. If there are broader questions, we'll get to those later. But yeah.
You just barely touched on before lunch, which was what if the data coming back, it's sort of the distributed case, what if you have partial information? And so I've got two control things, they each have partial information about the results of what's coming back, and how do you fit that into the framework, how do you model that?
Well, it basically is a matter of how you would model the control design and the system itself. So you might imagine that you have, let me just give you a simple example here. So suppose what we've got here are two systems that are interacting in some way and maybe making resource decisions separate. Well, let's see. We've got workloads that use basically resources of both systems. Okay, and then so these two somehow have to interact in some way, know about one another, so that, for example, we might have a QoS objective on requests that are coming in. This one is maybe doing maybe part of a query. This one's doing another part of a query. And we want to speed this up if this is too slow, or this doesn't have to be so fast if this is already fast. So that's sort of a very abstract kind of way of describing. You've got some sort of distributed coordination, resource management kind of problem. Okay, so how might you model this is the question. So let's say this is system A and this is system B. One way that you might do that is say, okay, I've got a box here. I'm going to have a transfer function for A. So I'll have a GA of Z and a GB of Z. And I've got something else over here which is going to represent some of the communication that's going on. So B is communicating with A. I'll call this, for lack of, that's communication for B. And this over here is communication for A. But this is all meant to be illustrative about, just showing that you have a lot of creativity about how you can use these diagrams. This is actually where a lot of the creativity does come in. And then what's going to happen here is then this communication here is going to be one of the things that's going to affect how this one behaves. So you might see that kind of interaction that goes on. Now we have to have a longer discussion about what this means. For example, what are we really doing here? Are we trying to regulate something? Are we trying to optimize something? To figure out how, and these are also, each one of these boxes is a single input, single output. So you've got to figure out what all that means too. But I think what it shows you is, and we'll see this to some degree in my, sort of hypothesized thoughts with singularity example, is that there's a lot of things you can do with these blocks. And all you have to do is just make sure you abide by certain rules. So one of the rules are each one of the boxes has a single input and a single output. You can put boxes in series or parallel. If you put them in parallel, the only thing that you can do with them is addition or subtraction. But then you can put as many things in series as you want. You can have many inputs, many outputs. But if you abide by those rules, it's all a linear system. And you can apply all these techniques. Once you go outside of those rules, then you need some other creativity to deal with it. And typically what we end up doing is we have sort of like a multi-state kind of analysis. And you divide the system up into regions in which they're linear. So that would be the approach it typically would take. There's a technique called gain scheduling that uses that kind of a notion as well. Okay, so you had a question first.
Yeah, so what would happen in this case if A and B had, say, differing or opposing goals, whatever that means?
Exactly. Right, so what would tend to happen, and let's, again, this is sort of loose here because there's a lot of things I haven't defined. All we know is that each takes input from the other, and there's a delay associated with it. Those are really the only things we know about that system. So let's suppose, let's even be simpler. Suppose they have the same goals, but there's a delay involved, and so one doesn't see what the other one has done. And so what you might expect is that when those delays get to even to be at a modest level, you're going to end up with an instability. If they have opposing goals, it's potentially even worse. Okay, other question.
So we always assume time is kind of flows constant, and there is probably some amount of difference of time between t and t plus 1 and so on and so forth.
Yeah, it has to be fixed. For this theory assumes that you have a fixed sample time.
But generally, at least in the big DB systems where I work, it's not a guarantee. You can always have some
Absolutely,
skew, and
right.
the skew can go up or down, and there's always all sorts of
Right.
But that and kind of what
Yeah.
effect.
I mean, there are different techniques you can use to do that. There are ways, and this gets to be a bit more sophisticated, but then we can't do just this simple discrete time analysis. We also have to consider continuous time. But then there are ways of dealing with basically translating the discrete system into continuous time and then looking what happens if you're using different sample times or different time points. And then you can do that kind of analysis too. It progressively gets to be more complicated, and so at some point you have to decide where, gee, I'm not sure it's worth the return I'm going to get on that investment. But not to say that there wouldn't be situations that'd be worth it.
Talk a bit about where you draw the line. Maybe like if it's 10% variance, maybe you shouldn't bother. I mean, you should consider to be.
Yeah, I mean, I think that's part of it too. And like when we build systems, we try to get some intuition up front about what the most complicated parts are, where the resource management problem is really going to be. So you say, well, geez, I'm less concerned about the individual accesses to memory, much more concerned about counting IOs. So we make those kinds of first order decisions. Okay, last question.
Is there anything that ties together queuing theory and control theory with regards to, I find myself using queuing theory a lot for
Right.
analyzing stages of requests as they get processed, but I intuitively I would think that the parameters of the queues in some ways could map to the poles and zeros and delays and stuff like that.
So there's a few things along this line. There's a paper by some folks who are doing this on web servers from, I believe it's Lund University in Sweden. And they have some simple queuing results that they've gotten from the literature on basically dynamic behaviors of queues. Okay, so they try and do this. If you're not familiar with Lund University, there's a fellow there by the name of Astrom, who's sort of like the god of control. He's written, I don't know, like 8 or 9 of the books on controls, and he's incredibly prolific. And Wittenmark is another fellow who is like the god of adaptive control. So,
Could you spell the first one?
Astrom. Carl, K-A-R-L. They're excellent books, but it's definitely written for people who are like mechanical engineers, electrical engineers.
Yeah, so it's pretty dense.
Yeah, they are dense. So that's one. Now there's another one I'll throw in if you're interested. There was a paper I did for I think it was one of the control conferences. I've forgotten which one it was. I think it was ACC, the American Control Conference, where there's some basic queuing results that relate utilization to autocorrelation. And when you think about it, a lot of these time series equations, when you talk about the relationship at time k to k minus 1, that's really about autocorrelation. And so it derived from, there are a few of these results having to do, one of them having to do with autocorrelation, another one having to do with relationship of utilization to batch size. So that gets back to the time notions. And we did a certain amount of stuff there with looking at just simple MM1 queuing systems and trying to relate the time series models to the queuing parameters. And if you send me a note, remind me, I'll send you the paper. Okay.
Maybe send it to everybody who's signed up.
Absolutely. I mean, in fact, what I think I should do, I'll make sure that everybody gets this stuff, and I'll look into maybe setting up a wiki or website or something where we can go to the stuff as well. Okay. Let's continue here. Slideshow. No, it's just slow. Let's see here. Okay. So, okay, now we're going to do the control analysis. Okay. All right, so let me set the problem here. What we're doing is, now what we've got, before we were doing is just showing how we could come up with an end-to-end transfer function if we had a feedback loop like this. Now what we've got is a slightly different situation where we've got maybe a couple of the components that we know. We know this system here, the node server, that's that equation, the node sensor, we've got this one. And what we want to do is design a controller here that will make it so that the end-to-end properties like settling time and accuracy meet our desired specifications. And the way we're going to do that is we're going to insert some components. So we can do it with the controller. We can do it other ways as well. We can insert like a transducer. We can insert a filter here. We can do something over here as well. All of these are different techniques that we can use when we design a control loop. So the thing I wanted to drive home here is, and we do this right now, is when you're designing a system, it's not just the controller design that you're concerned about. You insert a filter, well, that's another part of the system that you just put in there. You probably actually created some delays as well. And so it may be what you want, it may not be what you want. So you have to take this sort of holistic perspective. All right, so the way I'm going to start here is just talk about some of the basic controllers, and we'll see how they behave. So we've seen this controller here, this proportional controller. That was the one we had in the early example. Here's the time domain equation. We know exactly what this translates to in terms of z-domain using the stuff we had in before lunch. The integral controller as well. I mean, you can see what happens here. So we've got the intuition behind the integral controller is that the value of the control, like max users at time k plus 1, it's what you had before plus some delta having to do with the control error. So that's the constant there is k sub I for this for the integral controller, and p, the k sub p just looks and says it will take the absolute value based on the control error. So if you, for example, one intuition on this one over here is if your control error is 0, then that means the system's doing fine, and you shouldn't have, shouldn't change anything. Yeah.
The E k plus 1, so this is just a notation thing that I didn't capture before. For at time t,
right,
is the error for what you're doing at time t considered error at time t or error at time t plus 1?
The error at time t is the error actually at time t. So you look at the output at that instant, and you subtract that from the reference value at that time.
So how do you have the u of k plus 1 depend on the error at k plus 1?
Oh, because in this system right here, okay, so we get the output at time k plus 1. Okay, that's immediately subtracted from the input, the reference value, which is mostly constant for our purposes. And we do change the occasion, mostly constant. So we subtract it from there. We're still at time k plus 1. Okay, and then that then gets fed into here, into this, into the controller. Now,
being fed in make it k plus 2?
Now, we haven't changed any time yet. We only get delays from the systems. So, I mean, this system here has some delay. It's a first-order system. This system over here has no delay.
I think what maybe would make it easier to just substitute t for k minus 1 or something. So t
is that,
minus
is that the confusion you think?
Yeah, so u of t is equal to u of t minus 1 plus ki times e of t. So really, this means memory. The controller has a memory. It uses what it output before as its input to the next step.
Does that make sense? Is it my use of k plus 1 versus k? Was that the confusion?
Yes. Well,
it's just a matter of the time.
First order confusion.
Yeah. Okay, fine.
The second order confusion is if your error is the result of the processing of the system, then it seems like all you would get is e of t minus 1.
Right, so then you would have a different system. You should use a different model if that's the case. Right. If you have, for example, if you have a unit down here like a transducer that takes some delay, then you're absolutely right. You should put that in there. That's another component that will then introduce delay.
Can I test one assumption? I assume that E of k plus 1 is equal to R minus Y at k. Y from k.
R minus R, okay, E of k plus, okay, E of k plus 1 is equal to R of k at k plus 1 minus Y of k plus 1 in this system right here. Right. There's no delay here to get that. It says that the model here is that we can read the output and immediately compute it here. There's no delay. If we had a situation like that board over there, we'd have to put some other element in here because there's a delay in getting the information. Does that make sense? I mean, it's the model that's here, but it's, there are other...
It's not so much realistic.
It sort of depends. It depends on your time constants. If your time constants are large, and you have a local system with a local loop, and then you're talking about time constants on the order of a minute, but then you're concerned about interaction with other systems more distant. The more distant systems, you probably have something in here. The local one, you wouldn't.
But also, I guess, keep in mind, I think what your slide is trying to show has nothing to do with the model above. You're just saying that there's two different types of controllers.
Yeah, that's the purpose of the slide. Right.
An integral controller will always take that transfer function form, regardless of your control.
Right. Okay. So, and again, these are probably the two most basic kinds of controllers that you'll see. And what we're going to do is the progression for now till, make sure I keep track of time here as we go, until the next break. So I guess until 2 o'clock is going to be a series of design exercises. And really what we're going to do is we're going to start out, we're going to compare the characteristics of these two controllers. And they're very simple. I mean, in the real world it would be much more complicated, but they'll sort of bring into bear a lot of the concepts that we used and get a sense of what some of the differences are in the way these behave. And also sort of a notion of iterative design refinement. Okay, so what we're going to do here, I'm going to switch over to the spreadsheet. And let's see, actually I'm going to go back one slide there. All right. So if we... Okay. All right, let me just, I'm having, okay, so let's see, P versus I right here. And I'm going to go over this one more. Okay. All right, so...
Question?
Yeah.
You didn't talk about D.
No, I'm not doing D right here.
Because it's rare in software, or because of the audience you're shooting at?
No, neither one. The key, it's not rare. It's one of the most important things, and it's certainly not because of the audience. The key thing is, if you remember in that last section of the theory before lunch, we talked about composition. We looked at what would happen when you have a D in your loop, and if you looked at the poles, they were the same as if you had as if you just consider without D.
Oh, okay.
And that's the reason, because we're doing really just focusing on the poles right now. Yeah, that's the reason. Okay, so this is sort of a spreadsheet version of what we saw before. Here's the proportional controller. We see how the error is calculated. The key thing here is how the control input is calculated. It's Kp times EP of k, because the P here is just, it's intended to be a subscript, but it's just written the same case. And you'll see an I over here that corresponds the same way. So with the integral controller, we see it's UI is equal to, you take the last U, and then you plus this increment, which is Ki, the integral control constant, times the error for the integral control times K. The systems are the same. So that makes sense? We just go through briefly what the calculations look like here. Let's go across on the proportional control we've already seen before. So that's the reference input. We see here the error is just calculated within the side of the spreadsheet that does the proportional control. We're taking that B column, which is the reference input, and subtracting the measured output the Y. And you notice, based on your question over there, time, it's all on the same line. It's all 9, so it's all, and this is actually why the spreadsheets are so useful, because figuring out what the times, how they work out, is crucial. You get the wrong answers if you don't do the times right, and it's really important to sort that through. And you make different assumptions, you find out subtle differences in the model. Okay, the U, this reflects the calculation that's done by the controller. So we see that this is that constant at F8 over here. Yeah, you see the F column. I'm not going to move the cursor around too much, but yeah. You see the F column right over there. So F8 is where this constant is that we're multiplying the error by. And then Y is just going to reflect how the system behaves with that control input. Okay, that makes sense? And then over here, it's really exactly the same thing. We're getting, we have the same reference value, so that doesn't change. We get the subtraction here. The only difference is we're subtracting B8, but the difference is the output we look at is J9. So that's the this over here. So it's the output from the integral control system as opposed to over here we use the output from the proportional control system. Okay, and then what's different here is that we have the integral controller. So we have the I8, which is the last value of that control input, plus K8, which is the integral control constant, times the current value of the control error. And then the system is the same, just different inputs. Okay, so that's the way they behave. Now, we've played with this before, and we saw what happened with the proportional controller. Let's also take a little look at some of these characteristics here. So I think before we found that if we had some slightly smaller values for KP, we could make the system fast. We just have this problem that if this is our reference input, then we're off by quite a bit because I guess before I did 200. Let me switch this back to 200. Okay. So if we're off by, we get a 90 and we're trying to get a 200. So that's a bit of a pain. But it's really fast. So that's cool. Fast but wrong. Okay. So now over here, let's take a look at the integral controller. Okay. Are we lucky or what? Wow, must have just changed to take the right constant there. That's pretty cool. So what happens if we change that? How about if it's, I don't know, 2? Wow, converges there too. Okay, this is actually a property of the integral controller, very important property. And I'll show you why. I mean, actually it falls out of the analysis, and I'll show you why in a second based on the theory that you already have. But what we do notice is that it's not as fast as a proportional controller. Now maybe we can play with it a little bit and maybe make it better. I mean, maybe if we go lower, well, now we get some overshoot. You know, maybe if we make it smaller still, now that's real slow. So, I mean, at least if we're going to play with this, it doesn't seem like it's, we're fairly optimistic. I mean, actually, of course, you can do this through design. I mean, you don't have to play. We have all the framework, the background that's necessary to actually do this through design. But the takeaway from this is that we're able to get this accuracy over here, but it seems to be slower than what we can get over there. So, what can we do to try and get the best of both worlds? Okay? Integrate them, right. Okay, so before I go on and go back to the slides, so what can you tell me about this system versus that system in terms of poles and also steady state gain? So the integral controller, we see that it's slower. So what does that mean in terms of the poles of that system, that feedback system with an integral controller?
Closer to 1.
They're closer to 1, absolutely. That's what we would expect. And the steady state gain of the integral controller, what can you tell me about that? It's going to be 1. And that's because the output, which is that measured output over there, the Y, is equal to our reference input. And it's always equal to that as long as we're stable. So as long as we have a stable system, we'll have an accurate system, which is very nice. Okay, so now let's switch back to the slide deck. All right, so this was the summary basically of what kind of thing we have. We've got fast and not accurate, or slow and accurate. So, what do we do about that? Okay. So here's some analysis of this. I don't think I broke this down. Just let me see if I break this down better with an animation. I guess I do. All right. Okay, so that's our system. This is, okay, so here's, you remember that last section there where we did the basic feedback loops, and this is the simple one where it's just regulatory control, so the only input is the reference value there. And this is just for your reference. I think you may vaguely remember that this was the form of the transfer function from this input to that output. In the one that I showed before, there was actually an h of z as well, which was a transducer, but our transducer is 1. So that's why that falls out. So this is the form of the feedback system. So what the analysis is all about, it's about figuring out the poles of this. That's what it's about. Because once we saw before is that we can get, that'll tell us steady state gain, and, the settling time, and stability. The other part of the analysis is once we have this transfer function, we can look at this value at 1 and then figure out the steady state gain. And that will be our argument about whether or not it's accurate, or under what conditions. Okay, so here's what we got here. We'll take it a step at a time. Let's start with a proportional controller. Okay, so what we're doing here is we know this transfer function is the ratio of the output to the input. Okay, fine, those z transforms for the signals. Okay, we're just going to substitute in here. So k of z in the case of the proportional controller, it's just kp because it's just that constant for the proportional controller, if you remember from the slide before. That's the controller. And then we have g of z, which we're using, this is our system here, that's its transfer function. And then we've got 1 over plus kp plus the same thing again. If you sort that out and simplify it, this is what you come up with. So here's our poles. It's the places where this expression denominator equals 0. Okay, so it should be 0.43 minus 0.47 kp should be the poles. So if we take a look at that, let's go back, and I think what I'm trying to do is just show you, give you more of a feeling for how the theory relates. And go back over here. Okay, so that's 0.43 minus 0.47 kp. Okay, I think it's this right here. Yeah, 0.43 minus 0.47 kp. Okay, so this says that pole for this value of kp is 0.04. So it's very close to 0, like we would have expected. It's also a little bit negative. Okay, so you get some oscillation. What happens then when we change this? Suppose we change it to 2. Okay, bigger pole, also negative. Oscillation, longer settling time. What happens when we get to, I think we're looking at 3.1. I've forgotten the point at which it becomes unstable. Okay, that's unstable. What's the pole? It's outside the unit circle, right. So that's exactly what's going on here, this system. So the poles really, in this case, what we're looking at, really tell us a lot. All right. Now, the case for the integral controller, it's a little bit more involved, but it's sort of instructive in certain ways. So, I mean, you can follow through and look at the details here. I'm not going to, but you see you end up with a quadratic. So there are a few things that are sort of interesting here. I'm not going to, I mean, you can look at the math later at your leisure. One thing that's sort of interesting about this is you see what the Ki is over here. If Ki is small enough, you can actually end up with imaginary poles. Right? Because what will happen is this expression here will be smaller than 1.72. And so then you get the square root of a negative number, which is imaginary. So you can actually end up with oscillations there as well. So obviously this kind of system is a lot more complicated to explore. And that's where the poles are there. Okay, fine. Let me just leave it at that for now. All right. This is sort of a summary of what we just saw here. Okay, and we see for the different control gains what we come up with. We see that for the proportional controller, we come up with, this is settling times and then steady state gains. So the settling times, are, there's a somewhat of a drop, and then we're seeing a big increase here. Here we see a slightly more complicated behavior in part because of this quadratic, but the steady state gains are always 1 because of the nature of the integral controller. All right, so this was sort of a starting point, just to give you a feeling for what you can do with that analysis. What we're going to do now is sort of explore how we could make things better. All right, so here's one approach. Okay, so since the proportional controller is fast but wrong, is there a way we could compensate to make it fast and right? Well, that has some appeal. Okay, so what we're going to do here, we're not changing the controller. What we're going to do is essentially fake out the controller. We're going to come up with some additional thing here that's going to say, okay, you want 200? Fine. You think it's 200. That's cool. But I'm going to feed the controller something that'll make it think that it's something else, and it will try for maybe 300 but achieve 200. And that's called precompensation. Right? So we can do that. Go through and do some analysis here. Let's see here. Bring up the spreadsheet again. That's not the right thing. Get rid of that. And okay, here's the precompensation for the P controller. And let's go over here. All right, so what we've got here, now we've got the precompensator. And yeah, so 152 is the answer, you know that. But you got to figure out what the answer is. If you set it to 2, then it's too big. If you set it to 1, that's too small. So we've got this other design problem. We've got to figure out what the precompensator is. And I guess the other thing we should do is make this small enough so it's fast. So we want to design the precompensator for maybe 3. I guess 3 doesn't work. We could do 2.2, something like that. So that'll work. Okay, so now we have something that's fast and accurate. That's cool. But question is, how do you figure out what this precompensator is? And what are the implications of having a precompensator in your control loop? So go on to the next slide here. When you think about what's the precompensator doing, you're primarily interested in how it affects steady state gain, right? That's what you're interested in. So what we really want is we want this, whatever this precompensator is, we want it so that the transfer function times the reference input, which will be the measured out, which will be the output, times the precompensator is going to equal the reference input. So this is going to be the, I'm sorry, it's going to be, yeah, so this is the output. That should be y. But we want it to be the same thing as r. We want this and this to be the same. So that means these two things cancel out, and the precompensator should be 1 over, really, the transfer function. It's not surprising, right? Because we've got a transfer function that's producing 90, and we compensate for that by getting 1 over that, multiplying by 1 over that, because then the product of those two is going to be 1. Right? So, it's sort of intuitive. Okay, so like I said before, if we pick our KP at 2.3, then you do this, then then what you come up with when you do the math here. So with you substitute KP in over here, then you figure out what this whole thing is, and then you're going to end up with what P of Z should be. So this becomes 1 over 1.53, and so we want this to be 1.53. And that's exactly how we came up with that one before. So if let me go back to that over here. Did I do a calculation? Yeah, I did. All right. So let's try this here. So if this is, I have to remember what I said, 2.3 for KP, right? So if KP is 2.3, then what I want to do here is I want this calculation up there that's on the line right here. Because this is 1 over the transfer function. Okay, evaluated at 1. That's what I want. And that ends up being, if I reveal the secret here by changing this from a white font to, let's say, a black font. Okay, 1.52. It's the magic number. Okay, so if we put in 1.52 over here, or 1.53, I think it's closer to it because it was rounding. Right? So then I'm pretty good. Okay, now, if I decide, well, you know, I really don't like the way it settles and there's a lot of overshoot, I think I'm going to change the gain. Okay, so I'm going to change the gain to 1. Whoops, I'm no longer accurate. I'm at 140. Okay, so now I've got to figure out what my new precompensation value is. Okay, so let's again see what the secret number is. And the secret number is it right?
One more cell.
Oh, I'm sorry. Thank you. Thank you. Yeah, because the secret was hidden from me. Let's try this. Okay, so now it should be 221. Oops, did I get that right?
Yeah.
Okay, 221. All right, so then we put in 221 over here. 2.21. Okay, so now I'm back in good shape. Okay, so we can do this, but I mean, you know, it doesn't sound like the best way. It has its downside, certainly, because to be changing that. But if you figure out that this is sort of like a final optimization for the system, okay, I can do that. So fine. So we took care of the precompensation problem to some degree. All right. We still have this other issue, though, that the region in which this was fast, we were getting some overshoot. Okay, so how do we deal with the overshoot? Right, so we've got the precompensator. Okay, so one way of dealing with the overshoot is we can smooth things a little bit. So instead of taking the output as it stands, we've got this system over here. We're not going to muck with the system. We're going to essentially put in this control add-in, H of Z. And we're going to say what this does is this filters things so that what we actually see on the output is something that's smoother. Okay? Now keep in mind, all that I'm doing right here, right now, I'm sort of leading you through some application of the theory and some insight in terms of how you might do design incrementally. You wouldn't necessarily go quite this route. So don't take this as the gospel about how you go about it. But it's a great way of sort of for pedagogy to go through this. Okay, so here's one I might do. And the way I might smooth this is I say that my final output, T, you can subtract one from these time constants if that throws you. So this could be T of K times C of T K minus 1 plus Y of K. But the idea is I'm going to smooth it. I'm just going to take part of my current T and then I'll use that as a smoothing for what I'm getting for the actual Y. So if the C here is 0, then I get exactly the Y value here. And as C gets larger, then I'm taking more and more of the T and less of the Y. Okay, does that make intuitive sense at least?
Well, it seems like you've changed the measured output, but not changed the system behavior.
I've changed the measure. It's definitely a different measured output. It's a smoothed output. So if the system reaches steady state, if it's a stable system, the two systems will have the same steady state value. But their dynamics are different. Okay? So does the intuition make sense?
So I had a similar question to what David had. It's just that if you look at what the transfer of the GFZ was, you broke it up into there was a real system and then there was a sensor part of that.
Right.
What this feels like is that you took the sensor and then you just modified the output of the sensor. What we really wanted to do was to modify what the target system did.
Yeah, that could be. That could be. Again, this is intended to be pedagogy for an illustrator. I'm trying to make certain points, but you're right. You're right. I mean, that would be a better way in a real setting to go about it. But right now, all I'm asking you is not to so much say this is the way I would actually do it, more that you understand what it is that I did and you appreciate how it could be done differently, or probably even should be done differently. Because what I'm trying to do is also show you how the theory that we've developed, you can understand, you can see the implications.
Just to make sure I understand, this is a little delay, right?
Yeah.
And you're weighting the current sample and the previous sample.
Yeah, exactly. Okay. Exactly. Okay, so let's see what happens with this one here. And make this. So let's see here. That was, I'm going to have to look big because I can't see right now. Okay, precompensator plus filter, that's where we are. All right, so we have here, let's go through this. So here we've got our reference input has to go through the precompensator. The control error is computed as before. All this stuff is before, but we've added this t part down here where t at time k for this proportional controller is what we had, or k plus 1 is the way I wrote it here, is equal to what it was in the last time step, t at k, times some coefficient. Here's our coefficient over there that I'm sorry, this is the coefficient I was using, plus whatever the y output is. So if this coefficient right here, let's see, we can actually even do this. So if that coefficient there goes to 0, we got exactly the same system from before. And as this coefficient here gets larger, we get something that's more and more scaled. And that's actually sort of an interesting result. Let's see here. Some of these things here. Right. There's a certain characteristic to this system which is sort of interesting. Let's make it less than 1. Let's make it 0.9. Okay. Yeah, the y-axis is y, or the t, actually, t. That's what you're seeing there. The y-axis is
Are they always settling at 200?
Yeah, we can't see this.
Oh, I'm sorry. Here we go. Yeah. So no. See, what happened here? I mean, this is exactly the point. Remember, our intent was, and what we thought we were going to have here, was that we would still keep an accurate system. We would smooth it, but we'd keep the accuracy. We screwed that up somehow. Okay. How do we screw it up? What did we do wrong here? Okay, let me go back to the control diagram, and you can point to the block or think about the block that we did wrong here. And let's make this big. Okay? Well, the only thing we added was this. It worked before. It doesn't work now. What are we doing wrong? Yeah. All right. So this must have a steady state gain that's not 1. It must be a larger state. Okay. So let's analyze it. What's its steady state gain? Okay, so let's go on to the next slide here. Yeah, so why is it inaccurate? Blah, blah, blah. Okay, so let's look at the steady state. Okay, so we know how to convert this into a transfer function, right? So t at k plus 1, that's zt at k. This is just a constant. That's a zy of z. Do it all out, we come up with z over z minus 1. Its steady state gain is 1 over 1 minus c. Okay, so if c is 0.9, yeah, steady state gain is 10. Right. So the problem is that we need to redesign that filter. Or we could readjust. Okay, so that's a good point. We could either redesign the filter and make it steady state gain 1, or we could make it so that when we insert the filter, we also have to go back and adjust the precompensator. Either one will work. But for modularity purposes, I'm assuming that we would prefer to just sort of localize our effects. And we're going to focus, plus it works better with the pedagogy, so that's good. Okay, so what we're going to do is redesign it. And what we can do is change it just a little bit. And so we're going to have it, here's the form we're going to do. We want the steady state gain to be 1. So what we really need is when z equals 1, we came up with 1 over 1 minus c. We want a 1 minus c in the numerator. Because then it'll go to then it goes to 1. Okay, what does that translate into in terms of the filter? That means then that we have a 1 minus c for the yk plus 1. So we've got c plus 1 minus c for the yk plus 1. So basically, it also has an easier semantic too, because it's basically saying c is a number between 0 and 1, and you're figuring out how much you're taking from the last value of the output versus the current value of this output. Okay? So it actually is a little bit easier semantics, and then you end up with the right end result. Okay, so at this point then, that introduces our filter. Now, the problem is that the system also got slower. So it was inaccurate and it was slow. Here's the normalized filter. Okay, so we had 2.3 there. And now when we do it, we get the right answer because we have now the normalized filter, which is here. So that has the C and then the 1 minus C in it. Okay, so we've got all that, so that's good. The problem is that it's a bit slower than what we had before. So if we make this, if the coefficient there is 0.
Is that because the HEC had a Z term in it?
Yes, right. It's because there's a pole in the denominator. Right. So we've changed the poles of the system. We've added, because we add this filter, we've added a pole. We've made the system more complicated and added a pole. So here's if the C coefficient is 0, and then this is what we get. Okay, we get some overshoot. It's not smooth. We settle at 10, whereas here, right. So we're settling. Yeah. Okay. So we get we're smoothing. We're settling a little bit differently. Let me see here. Let me do this differently. One there. Oops. Sorry about that. Okay. Okay. In any case, go back to that. Okay. So you've actually already answered the next part of the question, which is why is it slower? Why do we change the dynamics of the system? And that's this analysis over here, which is essentially what you just said. We just went through. But let me make sure we're all clear here. So why was the system slower? The answer is that when we added this over here, what we've got, the poles of the system then, are the product of this times this entire system right here times this system here. So this entire feedback loop there. So that's this part over here, the poles, those three sets of poles. P has no poles because that's a constant. We know the poles here, that's a function of the Kp. And we added this pole at C. And so when C is large and we're getting the smoothing effect, then we also have, so as we get smoother over here, let me show you that. Let's change this to 0.75. As we get smoother over here, it's, we're also taking a longer time to settle than if we had essentially no filter at all. So 0 means no filter, and that also means that we have a pole at 0, which doesn't cause us any problem. And then as we get a pole, let's make it more dramatic, a pole at 0.9, let's say, and now we've got a long time to settle.
It's almost exactly analogous to adding a capacitor on the signal.
Yeah, exactly. Very similar to that.
The larger the cap, the smoother the signal, but the slower.
But the slower it is, right.
And the response now looks a lot like the integral controller.
Yeah, it does. It has a similar kind of effect. So what we did is we tried to sort of shortcut all that we were doing with the integral controller. So sort of the moral of the story is, well, geez, why don't we just go straight with the integral controller?
This one doesn't lock on to the value of R.
Exactly. Well, you have to play with it. You have to design it so that it will. You have to think about the precompensator and what that P of Z should be, what the constant should be. Okay, so that's sort of the moral of the story. You could go straight with the integral controller, or you could do these things in combination. So if you think of this is really two controllers in parallel. You got a Kp and a Ki, and so this is for the integral controller. This is for the proportional controller. And by having two constants here, then you get more flexibility about how fast you want it versus how smooth you want it. And that's the advantage. It'll be accurate because of the integral part. That anything with integral controller will have the accuracy property. But then you got this fast versus smooth trade-off, and you get more control. You get more opportunity there with the Ki and the Kp, and also the overshoot. Disadvantage is that, remember before when we were trying to find the values of Kp by doing sort of a search and just trying different values, we knew what larger and smaller is. Now we've got two of them. The space is larger. It's also more complicated because we end up with we end up with these two constants, and then of course the order of z's due to the integral controller. So that makes it more complicated to analyze too. Okay? So the purpose of this was just to give you a feeling about how you might go about this incrementally to do the design, and also sort of ground in a little bit more, steady state gain and settling time and how that relates to poles. and give you, somewhat of a feeling of then how you might actually apply this stuff. Yeah.
So I don't know if I missed this or not, but you showed us that we chose KP based on experimentation. There was no methodology used.
Yeah, originally that's what we did. Right.
There is scientific.
Yeah. There is, and in this lecture I don't go into design. This is just analysis. But I'll tell you what you would do for design. So for design, what you would do is you'd go back and you'd come back with the transfer functions. So let's just show you, we'll go back to that sort of complicated slide with the transfer functions on it. Okay, so here we have the transfer functions, and let's just take, let's just look at this one right here. Okay, so that's with the integral controller. So we have just one parameter, ki, that we want to look for. Okay, what we would do with our design is basically the following steps. We decide on some objective. We've got one objective we can work with because we only have one constant. So let's say our one objective is settling time. Okay? Now we know from the first order approximation that settling time is going to be -4 divided by the natural log of the largest pole. Okay? So from that we can invert back and figure out what that largest pole can be. Right? Because I've got settling time as my goal. I can take the inverse function of that and then figure out what the pole is going to be. Okay, now once I've got the pole, I've got this equation right here, and I can solve for ki for that pole. So I've got that pole there, and I just solve for ki. So that's the way you would go about this with a single variable. If you've got multiple control parameters, you need other kinds of techniques, and there's something called root locus analysis that was basically a graphical technique that was developed over a period of time. It's very effective at trying to give you some insights in terms of these trade-offs. There are also techniques, numerical techniques you can use for 2, possibly 3 parameters. Yeah?
Currently, these have very simple mathematical components for that produce these curves.
Right.
As you start adding complexity, presumably some of those become intractable, and you get interesting curves and so forth. In molecular simulation, molecular modeling, where you're doing essentially energy minimization on complex things,
right.
That's lots of dimensional spaces, and you're trying to get to what set of parameters fits your curves nicely. And one of the things people did was add AI to, it's starting to converge over there, let me just try something way over there and see whether that happens. Looks like it's going to 200, let me just go to 200 and set this value and see if that gets...
So like simulated annealing kinds of things?
Simulated annealing and that kind of stuff. And then things that would watch a simulated annealing and say, it's starting to go like this, let me put it like that and see if that's close, and then it's annealing from there. And so you get these jump steps. And I'm curious whether any of that stuff fits in
it could. I mean, you're talking about a whole suite of numerical techniques that might be applied. It definitely could. I mean, it's not something we've ended up using. I think that once again, you sort of, and this is always a challenge to figure out where you are, but at some point you decide, if I have to make it this complex, how does that relate to the system I'm designing? Am I modeling something that I'm sort of speculating about? And it's always a struggle to try and figure out where you are. At some point, you have to make this transition from essentially the science or the math to engineering. And whether these at what point do these techniques apply versus you should just go to engineering or try a benchmark or something else? It's a judgment call. But I mean, definitely you can apply those kinds of techniques. And I think one of the appeals here is there are a lot of these relatively simple rules, like with queuing, like rho over 1 minus rho for queue length. All the MM1 results, those are really handy in terms of giving you insight about what's going on in the system. And similar thing here, this -4 over, the natural log of the pole. I mean, that's a really easy thing to remember and sort of keep track of in terms of settling time. Okay, now I think I get to go. I'm just trying to make sure I stay on track here with timing. All right, so I guess our next break is after the real-world examples. Okay, good. All right. So at this point, I think I switch back to the applications. Okay, great. Okay, so now I'm going to transition over to show you the kinds of things that we did. which was the product-oriented stuff. All this is published that I'm presenting, so there's no IP issue with anything that I'm presenting, even showing you the papers. Feel free to ask questions. If you get to the point where I have concerns about IP, I'll just say I can't say. Yeah?
On your slides that I wasn't supposed to bring, the last slide it said go to the lab. Does that mean run the spreadsheet? Did we do that?
Oh, which one? I'm sorry, show me which one.
Just before here.
Oh, okay. Yeah. I mean, I'm not going to do that. Yeah, no, but sure. I mean, the spreadsheet, I think there are like 7 or 8 tabs. Feel free to play. And I mean, it's sort of fun to try and compare that stuff with the theory. Because, it's a simulation. And it should be using the same math, so that it should work out. Okay, so let me start with the utilities throttling problem. This is a fairly common kind of scenario, although I'm going to couch it in terms of database management problem. But basically the issue is you're doing something for production. In this case, running a database engine, handling queries, and you got some other background work that has to happen. In this case, it's like rebalance and backup and run CPU stats, running stats. And the observation is that a lot of this stuff, those utilities, if you let them run full bore, they have a huge degradation. It can have a huge degradation on performance. And it's not unique to database systems. I know Mario found this with Hotmail and things like CLR with garbage collection. I mean, there's a whole bunch of trade-offs here that you might want to make. So one of the key things. So now I'm going to take a bit of a step backwards, and what I do want to give you is a sense of what I thought were some of the key steps in attacking this problem. And this is really from the point of view of doing something practical, something that's actually going to be in a product. So what were some of the key steps we had to do here? Okay, so in this problem, one of the first things that actually took us a little bit of time is to ask the question, what's our control goal? What are we trying to do here? Are we trying to say that the utilities can only run for so long? Are we saying that they can only have so much resource? Are we saying that they have, is it a priority thing? So this is a combination of several things that are going on here. What we can do, we have the capability, we have the instrumentation and the effectors to try and do something. It's a matter of what makes sense, because these goals ultimately relate back to policies. We're going to surface this to an administrator. And we're going to say to them, look, here's what you can do. Here's how you can regulate your system. You're going to do it in terms of how much capacity that the utility has available to it. Does that make sense, or does something else make sense? So the one that we came on that seemed to work very well and seemed to be very sensible is to give the administrator the capability to make the following decision. How much of my production throughput am I willing to sacrifice so that these administrative utilities can do their job?
How does that mean for the administrator?
Because the administrator has to make this trade-off between how much they're going to, how much they want the system to do the sort of the survival kinds of things versus how much of the workload they're going to see, how much of that they can sustain. Now, it would be better to maybe make a statement like, okay, we're going to get your backups done by 8 a.m. tomorrow or by 6 a.m. tomorrow. But we didn't have the instrumentation to be able to tell you whether or not that was even possible. We couldn't control that. But what we could do is we could make a statement like this to give them sort of a qualitative feeling. They say, look, I'm sacrificing 5% of my throughput. The users aren't complaining, and my backups are getting done.
Is that an instantaneous statement, or is that a...
Well, the way it's controlled instantaneously, but the digestion of this and the implications of this have to be taken over a period of time.
Right. I guess that was the question, is that doesn't say the backups are getting done.
No, it doesn't.
That says we're thrashing the disk, and that's great.
Yeah, but right, exactly. It doesn't say that. And that's part of, so you're hitting the nail on the head in terms of trying to figure out what is this compromise between what you can do and what you would like to do. So we could do this. We could say we can guarantee you a certain fraction, that we can limit the impact on the throughput. But we couldn't tell them exactly when the backups got done. But they were able to work with that. They were saying, okay, fine, 5% doesn't hurt me too much. Okay, I can do that. And yeah, I've tried this over a couple days. That seems to work okay. Will my users take 10% because I want to have a margin there? Yeah, that works, but 15 is too much.
But in practice, they do want to know that there's a backup every day or something along those lines.
Yeah, I mean, right. And it clearly relates to how frequent, and there's a whole bunch of administrative policies go with this. Yeah, Mario?
Wouldn't it be possible to put another controller that adjusts X depending on, how close to the deadline you are? Like if you're close to 8 a.m. when your backup needs to be done, take whatever performance degradation you need.
Absolutely. I mean, this is a great example about other things that you might consider in terms of these policies. So this is an interesting thought. So suppose you have, and this is another level of control, another level of policy, and you decide how close do I have to be, or I could actually have what I could do. Actually, just with this same policy here, is I could have this be time varying. So my target at midnight might be or maybe let's say at 10 a.m. My target would be I'll sacrifice 5%. Once I hit 5 p.m., I may say, gee, yeah, I'm willing to go 10%. Once I hit midnight, I'll take 50%. And that might be another approach to this. So, I mean, there are many variations that you could do this, but this whole thinking that we're having right now, and you'll see this to some degree later on when we talk about some of the other examples, trying to figure out your control goals, that's one of the first steps and one of the most challenging ones. Things that you can do, which, you can, of course, expand the scope of can do by changing your system more, incorporating more, capability in terms of sensors and effectors, and what you would like to do. Okay. All right, so then we get to this issue about, okay, so what mechanisms do we have available? Okay, so this was backup that we're trying to control here. The top chart is throughput that you see in the production work, and the bottom chart is a kind of scaled version of priority. So what it means is that you're applying the control fully if you're at 1, and then not at all if you're at 0. So this was sort of we did the scale because it lines up with another chart over there. But from this point of view, from this chart, we're controlling CPU priority on a Linux system using NICE, and you can see that the effect on throughput it's almost no effect by varying priority, CPU priority for the backup utility, because it's not CPU bound. I mean, that falls in the category of big duh, but believe it or not, we had to spend some time and effort to prove that this was not enough, because then you get into these arguments that are a little bit circular that say, but wait a second, in order to do I/O, I have to have CPU. So if I control CPU priority, I can control I/O. Yeah, but it's not a CPU-constrained system, so you never have a problem with getting CPU. So that was the purpose of this exercise. Okay, so this led us to the conclusion that what we really needed was another kind of actuator or effector. We needed something else. So I had to do some work. And it turns out the way the utilities were structured, they tend to go back through a standard loop. This applied to backup and to the other utilities as well. And so it was relatively easy at the top of the loop to have a check to see if there was a delay that should be taken. So we call this self-imposed sleep. So when you got up to the top of the loop, you weren't holding any locks, weren't holding any other resources. So if you went into a sleep, you supposedly weren't going to hurt anybody. And so then with this mechanism, then the effector would be then the control then would be about controlling the amount of self-imposed sleep. And so here what we see is, again, it's the same scale, 0 to 1. From 0 is no control. In other words, you never sleep, to 1, you're always sleeping. And so you can see what happens with throughput. So when we never sleep, the utility never sleeps, you get low throughput. And when it always sleeps, you get high throughput, and the other stuff is in between. So the general shapes of the curves look comparable, but there are shifts that happen There's some dynamics associated with this because it takes time for the utility to get to the top of the loop, and so you may change that value, but it doesn't mean it happens instantaneously. And the other thing is just the normal thing that you see in systems where every now and then strange things happen, and you get things that go a bit wild. But that's but the general shape of the curve here certainly looks much better, and so that looked like a reasonable mechanism for being able to adjust the progress of the utility. Okay. At the top of the loop for the utility, yes.
Utility, but not in the main system itself.
No, not in the main system itself. It's just the utility, because we're regulating the utility. We want to be able to make a statement about how fast it goes.
But many of these utilities were written without the statement there, right?
I'm sorry, many of the
utilities don't have that inherent statement.
You have to, right, we had to put it in. We had to change the code.
So the other thing is, a lot of times the systems are not CPU bound because we're operating them at a low CPU utilization just to account for those spikes that happen once in a while, right? So the issue that runs into a lot is it's at the point of those spikes that we really want these utilities to back off. Right.
Right.
All of a sudden, the spikes happen unpredictably, and they also are very short duration.
Right. Exactly. And so you have to decide. This goes back to the notion of what your goals are and what you can achieve. So with the sampling rates we're dealing with and the control rates we're dealing with, these really would have to fall into the category of disturbances. The things that are unexpected given the setting of the control, but it sort of will perturb the controller in terms of what the effect was of that last control setting. So it's a disturbance. I mean, what you can do is you can run the controller faster. And so instead of doing this, I think we're doing this like every minute or so. I mean, you could try and run it every second, but then your overheads are huge. And then there's a lot of other dynamics. You may start seeing some scheduling dynamics that cause more of a skew. So instead of these peaks lining up, you might see this is shifted more to the right. So that's sort of the kinds of trade-offs you face in this sort of design. And it goes back to this discussion about sampling times and control frequencies. Okay, so the next thing was, so we got the goal. We got a reasonable effector. I'll gloss over the issue of the measured output, which turned out to be a challenge in and of itself. I know it's something Mario is challenged with as well, is what is it that you measure that's reflective, but we eventually came up with something. Now let's talk about the block diagram here. So some of this we're familiar with. We've got the DBA that's going to think in terms of the reference input is going to be what sort of degradation we're willing to accept. So am I willing to accept a 5% degradation, 10% degradation, whatever that is. Controller, we used a PI controller. That was the last one that we saw in the series of things. So it wasn't, that per se wasn't terribly interesting. What was much more interesting was to try and figure out how we're going to compute this degradation. You see, we're running a utility. And so the throughput we get is a combination of the nature of the work that's being presented to the system and the effect of the utility. Now, one approach so we know what our current output is when we combine the utility and the work. What we don't know is what the degradation is, because that requires for us to essentially subtract the effect of the utility. Okay, so one extreme and simplistic proposal was, okay, every 10 minutes we'll stop the utilities and then run just flat out and see what our baseline is. Well, a few things here. First of all, you could waste some resource capacity doing this. And secondly, just because you did it 10 minutes ago doesn't mean it's necessarily reflective of what's going on right now. So that wasn't terribly appealing. So what we ended up doing instead is we said, look, can we come up with, is there enough variation in the way we're controlling the utility? The technical term is something called persistent excitation. Matter if you're changing the nature of the control enough so that you see a lot of variation in the output. Is there enough variation here so that what we can do is actually estimate the effect of this control, the self-imposed sleep, on the measured output, which was a page kind of measure. If we can make that estimation, then let's figure out what the output would have been if we were at a control setting we were never throttling the utility. I'm sorry, we were always throttling the utility. Because if we're always throttling the utility, that throughput that we would get is our baseline. So we have to estimate this model, then we solve for the model at the point at which we're always throttled, then we can compute the degradation, and then we can look at then how we're doing. That's essentially all this is transducer. This is all transducer right here. And then that allows us then to compute the difference relative to what the DBA wanted to see. So just to sort of fill in the blanks a little bit there. Okay, so that's percent impact, that's pages per second. Yep.
So compute degradation has two inputs.
Yes, it does. And that's, yeah.
It subtracts, though.
Pardon?
It's just a subtractor, isn't it?
Yeah. You'll see what it is. It is a subtractor. The block diagram should have been drawn differently. There's no reason why it has to actually be a two-input box. Thank you for pointing that out. I should have drawn that as, you can break that apart. But you're absolutely right. It's just, what it really is it's a circle with a subtraction in it. Yeah. Okay. Okay. And then, so that shows you the part about computing the linear effects, and then this is with the various computations that we did there. Okay. So this also goes back to the point of this model estimation over here. These points that you see here and these estimates, this is all done online. We didn't, I mean, you couldn't do this offline and get anything that was going to work for a production system. So we used a technique called recursive least squares to look back at the last n values and essentially then computed what this slope was.
Things are zero, they really are not linear, and then the linear part only comes in once.
I mean, you're right.
Stable,
You're absolutely right. I mean, it could be, but this goes back to giving you sort of a qualitative feel about how you do this design. So, I mean, again, there's always this transition from the math to the engineering. So, to give you an example for what we did over here. So, here's some examples of some benchmarks that we ran. Okay, here is this is a measured output. It's in units of pages. You see the green over there. That's when we ran it with no utility present. Then we ran it with the utility present and the controller on. And this is the target that we came up with over time, because depending on, you see, our baseline varies depending on the nature of the work being done. If it's, we're backing up more during some periods versus less. So that's why this target, if you look at it in terms of units of pages, actually varies a little bit over time. And if you look at how well we did in terms of regulating the measured values relative to the target, there was a little bit of startup there. I mean, there is variation around this, but the idea is not in this particular example to be dead on, just to give the administrator some control. And it's sort of this trade-off between, here's the throughput I could get if I didn't run the utility at all. Here's what I am getting, but I'm making some progress with the utility. So again, this is sort of intermixing of science and engineering, making a judgment about what seems to be qualitatively reasonable. What's really bad is to give a customer a knob that you turn it and there's no effect, or you turn it and it has a counterintuitive effect, or you turn it and it's a nonlinear effect depending on the position of the knob. Those are really bad things.
The cool thing I got out of what you did was lots of times we look at the way we do our experimentation is by trying to do, eliminate some variables and so on. So we try to run the system without this load, and that's the only way we think we can get baseline. I think what you seem to have done, which is neat, is you said, if just when I'm operating with those variables in there, I'm able to deduce what the zero value would have been just from the inherent variation of that variable. So you don't have to actually turn it off.
Right. You don't actually have to turn it off, and which was a neat trick under the circumstances. Now, let me point out something, because there's a subtlety here which may not be altogether apparent. And this is sort of inherent in any sort of adaptive control. I use this word, persistent excitation. Okay, let me tell you what that means here. That means that suppose my control is really, really good. And so what happens is that I essentially have a zero error term over here. And so as a result, I'm keeping this at a fixed setting. Okay. Well, I'm not going to be able to figure out a curve like this because everything is right in there. Okay? And that's why that's this little trick where, and that's why you see some of those bumps up and down. You want to vary U a bit. Because if you don't, you can't get a reliable line. Yeah, Mario.
Is there any guide on how to do that variation?
How much to do the variation?
How much and how, normally distributed values?
Yeah, there are a few sort of rules of thumb on this, and but I don't have, I don't, from our perspective, this was one of those engineering decisions. I don't know that I don't know that it's been thoughtfully gone through, and part of it sort of depends on how much you're willing to sustain in terms of variability, around the target line. How important is that to you? Because that's going to be the trade-off, right? The more you vary that U, that means the more you're going to affect the actual degradation that you're getting relative to your target, because you're sort of working at cross purposes there. Yes?
So did the transducer transfer function turn out to be anything interesting, or was it just constant?
No, it wasn't. That per se wasn't very interesting. It was all zeroth order stuff. Yeah, and that per se, we tried fancier things, but they weren't important. Yeah.
Now, in this case, the backup is something where if I didn't provide backup, the server continues to function.
That's correct. Absolutely. Absolutely.
With utilities that are required, for example, garbage collection.
Yep.
Such that if you don't do it, you run out of space and crash.
Right.
So it's not like you can just say, I only went 5% today, and it's meaningful. You have to do it.
Yeah.
And you're looking for and indeed, if you don't do it, that affects performance. And whether you have any systems like this where what you were trying to achieve was trading off running your utility versus the performance gain of having run your utility, and so you're optimized. It's an optimization at that point, not a regulation.
Right. So the garbage collecting one is actually a bit more extreme because there's a problem with failure there. But it's fair. If you run it in a little shorter interval, then it's more of a performance optimization. Another one in the database world is statistics. Collecting table stats. Right. That's a one where I think it's probably even more of you're not going to fail, but clearly you're going to get a degradation. So in both of those cases, it's clearly an optimization kind of problem, but it's not something that we really approached as that in the work that we did, because we ultimately did do a number of utilities. But I think that framing it that way would be interesting. We didn't do it that way, though. Okay, so this is one of the world's most, I should probably, the only thing I want to give you out of this is that buffer pools are important in database systems. So I've presented this to a variety of audiences, but to this audience it's sort of, probably one of the world's silliest slides. Okay, so this is just in the way of background. We have multiple buffer pools, and you want to be able to, there's multiple buffer pools, and there are multiple types of memory, like lock memory, sort memory, join. There's a lot of different kinds of memory. And what you would like to do is be able to allocate those in a way so that you maximize overall throughput. Now, this is a little bit of a challenge because it's a more complex situation in many ways. First of all, there are different kinds of workloads that you may be dealing with concurrently. And so you may be interested in more of something that looks more like a constraint rather than overall maximization. Potentially the memory pools are there just to protect certain classes of workloads. So it's not necessarily that you want to level out everything. So there's some issue there in terms of how much leveling you actually want to do. The other thing, which is a bit of a subtlety here, and we're going to get to one of those boundaries where I can't give you too much detail, and that is that the way we were able to proceed with this was predicated on a capability that DB2 implemented so that if you allocated memory to a pool, not only would you get information about size and some degree of response times as it currently stood and as it went over time, you could also get information about what would happen if I added additional memory. How much would response times drop? Okay, so they had a little bit of a simulation analysis engine in there as well. And that was actually crucial for us because that was our sensor measurement. What we were trying to do is balance the incremental change in response time, because that's what you're interested in. You add more memory, what's the effect going to be on response time in what time period? So that was.
So you always assume that prediction is accurate.
We did. I mean, and the end result of this is you look at how it plays, on the actual response times, right? But because if that is wrong, then you obviously have a problem, right? Okay, so let me explain this diagram, because this was our corresponding control diagram here. So this was a case of a multiple input, multiple output system. The inputs, what we're controlling here, were the amount of memory in each memory region. So whether it's a buffer pool or a lock list or a sort list or whatever. That's what we're controlling. And then the outputs from this were these incremental response times. And what we're trying to do is balance those. So the control goal here was actually trying to minimize those incremental response times, which should also ultimately then maximize throughput. So the way we did that balancing of the response times is that the reference input for each one of these controllers, for each one of the resources over here, the reference input that we used was actually the mean value of all these response times. And so if we could drive each one of the memory pools to the mean value, then we've got it balanced. And that's the technique. That's what this diagram says here. Since this is a multiple input, multiple output system, yeah, go ahead.
If you've got it balanced, that could be a local minimum.
Right. Doesn't guarantee you it's global, right? But it is a local. Right. So depending on the shape of your, response time surface, you did well or you didn't do well.
Right. You could imagine getting stuck in a local.
Oh, absolutely, absolutely, and that's a fair comment. And here's another great example of wow, let's try some experiments here. Do we need to be more sophisticated? Let's see what happens with customers. Are there workloads such that we really have to be more complicated? And that's a great example of one. Okay, since this is a multiple input, multiple output system, there's some additional dimensions to how you do control that are sort of interesting. And especially for this kind of system, because we've got this sort of inherent trade-off here between minimizing the response times by being accurate in the regulation. By accurate, I mean we've driven all of the response times, incremental response times for the pools, to the same value. That would be accurate. That's corresponding to the accuracy problems we saw before. But there's another challenge here too, and that is we've got some cost associated with our control. This doesn't come for free. We move memory from one pool to another pool. We've got to write some stuff out, and we've got to warm up the other pool. So maintaining that balance between the two was extremely important thing to surface, and that's what this linear quadratic regulation is about. So this overly complicated expression, let me explain what's going on here. These E's here are two aspects of the control error. And one is the sort of the cumulative error, and this is the instantaneous error. And what we did is we figured out the design, the control design, is about figuring out a weighting factor Q that's used here to indicate the accuracy versus the weighting factor R over here, which is about the control frequency. So the more control you do, the more you're going to hit throughput because you're thrashing things around. And how much does that buy you relative to the accuracy of the control here, which is going to minimize your throughput? So that was the way we handled that one. And in the series of papers in the beginning of the section, you'll see some references to some that deal with cost of control specifically. And I think those were at the, I think that was at the American Control Conference that we discussed that. Yep.
quick, what keeps them from being multiple independent controllers driven from the same average output?
Well, you answered the question.
I see the multiple inputs. I mean, but where are the multiple outputs?
Okay. Yeah. So, okay. Let me clarify something. The system is multiple input, the target system is multiple input, multiple output. The control loop itself is self-contained. I mean, you can argue that the inputs here, we've got some disturbances, but yeah.
I guess my question's over on the E side, E1 through EN.
Yep.
And the load balancer. Does that load balancer control, when it decides to set an output UN,
right,
is that driven by anything other than EN? It's also driven by the other E1, 2, 3?
Yeah, well, the controller's this design right down here, so you can see what all it depends on.
Oh, of I.
Yeah.
Okay.
And it's trying to
Yeah, it's an optimization. It's
trying to optimize that equation.
Right, exactly. It's trying to optimize that equation. Right. Okay, so again, this was something that was a great thing to publish, but it wasn't really, this part of it was not real. I can tell you the real part, though. Okay, so this was with H, and what you see over here is that we have a case here where things are highly unbalanced, and so you see long delays on one query, and then the other one's very short, and you balance it, and then the total response times are much better. And so with this particular extreme case, it was a 59% reduction. But we actually, for the database people here, we did this with the C benchmark, and actually got 3% improvement in C, which is a lot for C. So it was a real thing. It actually did go out as a feature, just like the utility throttling stuff was actually provided real value. Okay, so we're just about at the end of sort of the formal presentation part. I'll give you sort of a summary and some pointers and stuff here. And then the next part after the break, we're going to talk about Hotmail and also Singularity. And really what that's about is to give you much more of a feeling about how your colleagues are thinking about or trying to go through this. I think with Stathis it's more that how I think he might. So, okay, so this is a summary. So we talked about and went through quite a bit. So sort of the logical structure of control systems. Some of these issues here about what the criteria are you might want to look for. How many people here remind me? How many had seen Z transforms before you walked in the door today? Okay, so about half. All right. So in the rest of you, it's something really different. You picked up tonight. Super. Okay, and we saw the control analysis. Who had done control analysis before they walked in the door today? Okay, a little bit fewer. All right. So you got a feel there for the kinds of stuff there. Let me show you just some of the, okay, so this is that one page, everything you ever wanted to know about control theory, at least simple linear theory. So there are a number of texts you can look at if you dare. So if you're interested in an introductory text in control theory, just to see what like mechanical engineers study, the Ogata book is a standard one, and Franklin Powell. These are probably two of the most widely cited ones. But I'll tell you, you open up the book, and the first thing they're going to do is Laplace transforms. So and you get to learn all about dash pots. So if that's helpful to you, hang in there.
That's just because they live in a continuous world.
Exactly, right. Exactly, but I think it's even more than that, Hassan, because what they do, and it's a very reasonable approach, is discrete control. Discrete time control was it came next. Yeah. You start with continuous time, and then when you talk about sampling it, then you get to discrete. And so you have to understand continuous before you can get discrete. We said nothing about continuous time in this lecture today. Did it all, and it's all based on the notion that Z can be interpreted as a shift operator. If you have that intuition, then you don't have to worry about continuous. Now, if you want to talk about changing your sample times, your control frequencies, you got to go back to continuous. And then there's a whole bunch of other stuff that comes in. But we can get really far without even doing that. Okay, so let's see. The adaptive control stuff, you see, I guess, do I only have one book by, I got a couple with Ostrom. So this is Carl Ostrom, and Wittenmark is a fellow for adaptive control. I mean, there's a whole field of nonlinear control. There's stochastic control. Oh, there's another one with Carl in it. There's AI-ish stuff with fuzzy control, and this is sort of simple control. So I do. If you're interested, I have a sort of informally, I can give you a pre-publication draft if you just want to look to see what the book has in it. Okay, and then there's a variety of places where this stuff has been applied. The TCP/IP stuff that Chris Hollett did with Don Townsley got a lot of play for a while. And it ultimately, there's a group at Caltech which maybe isn't on here. Yeah, I don't think that they're actually on here. Wittenmark and a student here, Anders Robertson. If you're interested in some of these like dynamic queuing stuff, that's what they were using. So this paper, I believe, even has some of that stuff in there. Okay, so that's this part. Why don't we come back in about, we give you a little extra time, like 20 minutes or so, give a chance to get a drink of water and stuff, and then we can, yeah.